Okay, cool. So let's go on to question 3. Right, so below is a sketch of the curve S with this equation. The curve crosses the x-axis at the origin at the point A0, okay, and B0, blah, blah, blah. Right, okay, so everything that they say here is summarized in the graph by sort of putting the points on and labeling them. So if we now go down, it asks us for what are the values of A and B. So A and B occur when y is 0, and we know this other one is in fact the origin. It says so in the question, it shows it here. So if we put in y as 0, we get 0 is equal to x cubed minus x, and we can factorize that quite nicely. So it becomes x times x squared minus 1. This is a difference of 2 squares. This becomes x, x plus 1, and x minus 1. So it tells us the solutions here. The solutions are x is 0, x is minus 1, and x is 1. So that means that b must be 1. So that must be the point 1, and this must be the point minus 1. Okay. So by completing the square or otherwise, find the value of delta. Okay, so delta is here, here, and here. Okay, so it's a sort of unique y, and the special thing about delta is it's sort of on the end of these things here. So the special thing about delta to me is that if you took an x, it is an x for which you only get one y. Okay, so it's like a special case of x's for which you only get a single y. All of the others, you either get no y's or you get 2 y's. Okay, so if you took an x here, for instance, you would get this y solution and this y solution. Okay, so what we can do, I think when it says complete the square, we're completing the square for y here, which I know is unusual, but still it's fine. If we do that, we get y minus 1/2 squared. Okay, so that will give us a y squared minus y. But it will also give us a plus 1/4, which we don't want. So we're going to take away that quarter. And then that's still equal to that x cubed minus x. So if I rearrange this for y, you can see this a little bit clearer. It will become 1/2 plus or minus the square root of x cubed minus x plus 1/4. Okay, so when y only has one solution, it means that this sort of curve under here is actually equal to 0. So we know that the solutions to this equation that give 0 are alpha, beta, and gamma. And at that point, y equals 1/2. So that's sort of true. We know that sort of delta is 1/2 because when this bit under here is 0, we only have one solution for y, and we only have one solution for y for a particular x only at these delta points. Okay, otherwise we have 2 or no solutions. So we actually know that this x cubed minus x plus 1/4 is negative in this sort of range here, and in anything less than -1, anything less than delta. Okay, sorry, than alpha, then it's negative as well. Okay, so we found the value of delta, and I guess it says or otherwise, and actually there's quite an interesting way to do it or otherwise. So if you considered differentiating this, you could differentiate it implicitly. So I'm going to differentiate it with respect to x. Okay, so if I differentiate it with respect to x on the other side, I get 3x squared minus 1. And if I differentiate with respect to x, I need to do this implicitly. So I can differentiate with respect to y. So I can actually write this as, if I want to differentiate something with respect to x, I can differentiate y with x, multiply that by dy of y squared minus y. Okay, bear with me here because there is a reason I'm doing this. In fact, something we can see is that the gradient of this curve is infinite or negative infinity at these points alpha delta and at all the points where y is delta. So if I differentiate this, I'll get a form for dy dx is equal to, that's going to be 2y minus 1 in there. So this is implicit differentiation. If you haven't covered this yet, don't worry about it. You probably won't need it. So if I then look at this curve, so I'm looking for where this would diverge, where this would sort of not exist, the gradient is it's going to be sort of infinite, then it doesn't really matter what's on the top, 3x squared minus 1, but what will be on the bottom is 2y minus 1. And so y equals a half gives me those sort of divergence in gradient, and those occur only at the points alpha delta, beta delta, and gamma delta. Okay, so that's another way of getting to that solution. You could even, if you wanted to, flip this, right, dx dy, and say that that is going to be equal to 0 when 2y minus 1 equals 0. And dx dy is like saying if you sort of rotated this whole thing by 90 degrees, and you sort of think about where dx dy is sort of 0, then that's kind of like saying where are the stationary points on this graph if maybe if you sort of rotated it around. Okay, but anyway, that's sort of two different ways of doing it. Because there's an or otherwise there, I always like to give some options. Okay, so explain why the curve is symmetric about y equals delta. Okay, so we've got to explain why it's symmetric about that point. So what are the transformations that we're going to need to show that this is symmetric? So what I would say is when you're doing something, finding out if it's symmetric about a certain line, and there's sort of a specific way of doing this. I'm going to sort of draw this again down here, so I can draw several lines on here at once. So we've got a curve that looks something like this. I might sort of okay, and it looks something like, okay, this is just a rough sketch, so it looks something like this. Okay, and then there's a gap, and it does this. And we know that this this line here, oh, that's a really rubbish line. Let's do it like that. This line here is delta. Okay, y equals delta. Okay, so y equals delta. So if I want to show that it's symmetric about that line, I need to think of a series of transformations that actually reflect about this line and show that the reflection, these transformations, don't alter what the equation of the line is. Okay, so the first thing I could do is reflect it in the x-axis. Okay, if I reflect this in the x-axis, I'm going to get something that looks like this. Okay, so it will come down here, and sorry, I'm just going to draw this. It's going to do this. Just give me a second, I've got to get this right. Okay, comes up like that. Okay, and now this line here, let's draw it on, is going to be the line y equals negative delta. Y equals negative delta. So if I then shift this graph up by 2 delta, that would be equivalent, so sort of plus 2 delta here. So shift this graph up by 2 delta, that would be equivalent to, in fact, a reflection about the line y equals delta. So let's try and show that under these transformations, the graph or the equation of the graph doesn't change. So I can do that. y minus delta. I'm just going to use delta rather than a half because you might not have got this part correct, and so you want to still have something. Okay, so don't put it in a half, put in a delta, and you've said what delta is, and that's fine. Okay, so that's what we get here. So I guess I'll call that a quarter, or you could call that delta squared if you like. Okay, I should really choose. Let's use a half. Let's use a half. Okay, so if you didn't get this part, you can do this by just putting in delta here instead of 1/2. Okay, right. So let's have a look. What can we do? So to reflect it in the x-axis, that is equivalent to changing y to negative y. So the transformation of y to minus y is reflection in the x-axis. Okay, so that will give me this curve, which rightly has a different form. Okay, I'm just going to put dot, dot, dot there. Okay, and then the next thing that we could do is, what did we do then? Then we added 2 delta to the in the y direction. So that's kind of a translation upwards by 2 delta, and usually you would write this as x minus. Usually we write this as x plus 2 delta. Or f of x plus 2 delta if you were doing a sort of y equals f of x. But if you think about that, that's equivalent of doing y minus 2 delta. Okay, that's equivalent of doing a y minus 2 delta. So if I put that in, I'm in fact going to get minus y, and instead of this y, I now put y minus 2 delta is y minus 1. Minus 1/2. Minus 1/2, and then that's all squared. So if I simplify this, if I expand this bracket, I'm going to get 1 minus y minus 1/2 all squared, and that becomes 1/2 minus y squared. And in fact, that is equivalent to what we started with, okay, because y minus 1/2 squared is the same as 1/2 minus y squared. So these steps, I probably should say at this point here, I am translating by the vector, which is 0 in the x, but plus 1 in the y, or plus 2 delta in the y. Okay, so those 2 steps, reflecting in the x-axis and translating, they are equivalent to reflecting in the line y equals delta. And as we've shown that the equation is invariant under these 2 transformations, or under this whole transformation, then we must be symmetric in that line. That must be a mirror line on our graph. Okay, so we proved that part there now. Find a cubic equation in x which has roots alpha, beta, and gamma. Your expression for the cubic should not involve alpha, beta, or gamma. Justify your answer. Well, actually, we kind of justified this earlier when we looked at this bit here. So when y equals 1/2, x should equal alpha, beta, and gamma. Okay, those are the 3 points that it could equal. And when y equals 1/2, we know that that expression underneath the square root must equal 0. So alpha cubed minus alpha x plus 1/2 must equal 0. And the same is true for beta, and the same is true for gamma. So those are the three roots to this equation in x. So that is your justification for this, that in fact x cubed minus x plus 1/4 equals 0, I guess, has roots alpha, beta, gamma. Okay, What does it ask for next? Okay, so by considering the factorization of this cubic, find an equation for alpha plus beta plus gamma. Okay, so if I want to write this factorized, I would write this as x minus alpha, x minus beta, and x minus gamma. Okay, and if I was to expand this, the first thing I get is x cubed, but then to get an x squared term, it would be something like minus alpha times x, and you can do the same for beta. It would be minus beta times this x, and then lastly it would be minus gamma times this x times this x. Okay, so you could have minus alpha plus beta plus gamma. That would be your x squared coefficient. Okay, but you can see here that we don't have an x squared coefficient. So it must be true that alpha plus beta plus gamma is in fact 0. So alpha, beta, gamma equals 0. Okay, lovely. So let's have a look. What's next? Let C denote the circle which has points alpha delta and beta delta as ends of a diameter. Write down an equation of C. Show that C intersects S at 2 other points and find their common x coordinate in terms of gamma. Okay, so it has... Okay, so where's the center of the circle? So the center has a y coordinate of delta, and its sort of x coordinate will be sort of the mean of those two alpha beta points. So or the sort of midpoint, which is alpha. Actually, let's have a look. Just be careful here for a second, because alpha plus beta. Yeah, so yeah, I'm just being careful because I was thinking about the diameter, and one of these numbers is negative, the other number is positive. So I've got to be careful there. Yeah, so this is alpha plus beta divided by 2. That'll give me my center, my midpoint. When I'm looking for the radius, though, then let's see what the diameter would be. The length of the diameter would be beta minus alpha, because alpha is negative. You want to find that distance between those 2 points. And then, so if I want the radius, I need to divide that by 2. So that's equal to my radius. Okay, so putting that into the normal formula for an equation of a circle, I get x minus alpha plus beta over 2. I'll put that in brackets. And that's got to be squared, plus y minus delta squared equals beta minus alpha over 2 all squared. Okay, so there's my equation of C. So I'll just do C dot dot. Okay, what did it ask for next? Show that C intersects S at 2 other points and find their common x coordinate in terms of gamma. Okay, so I think what they're going to ask us to do is substitute in for this again to give me a sort of something with just x. So we're looking for where the curve y minus delta squared, that is equal to x cubed minus x plus 1/4, okay, or delta squared. So that is equal to this y minus delta. And if you're looking for where 2 curves intersect, you want to treat them as sort of simultaneous equations and try and sub one into the other. So that's what we're doing here. We're subbing one into the other, and we're actually going to find that now we're going to get something, or we're going to get another cubic, but this cubic might actually have an x squared term, because when we expand this x on this side, we're going to get an x squared term. So we actually know 2 of the solutions to this equation, 2 of the solutions to where the circle intersects the curve up above, and they are at alpha and beta for x. okay, because they told us that they're the ends of a diameter. So I'm going to use gamma 1, a new gamma, or gamma prime maybe, to denote the third solution. So because this is a cubic, it can maximally have 3 solutions, and that tells us that we have 3 roots of this equation, and the third root has two sort of y coordinates. It crosses at 2 points that have a common x coordinate, because as long as that third root isn't equal to alpha or beta or gamma, then we know that the curve from up above has more than one y solution for any point that isn't x equals alpha, beta, or gamma. Okay, so I hope that is clear. Let's expand this and see what we get then. So we get x cubed from this bit here, plus x squared, and then we get, we've got to square this, or sorry, we've got to square this bracket out. So we're going to have a minus alpha beta minus 1 for my x term. So that I'm going to call minus alpha plus beta plus 1 x. Okay, and then we'll have an alpha plus beta over 2 squared minus this plus 1/4. So if I do all of that, I'll get alpha plus beta over 2 all squared minus beta minus alpha over 2 all squared plus 1/4 equals 0. Okay, so now we have an x squared term. So I said that this, this cubic should have 3 solutions. Alpha and beta are definitely still solutions because it touches, right? It touches the ends of the diameter, touch the other curve at alpha and beta, right? But then I'm going to call this third solution gamma prime, and that's just to distinguish it from gamma. So they want me to write this third solution, gamma prime, in terms of gamma. So I know that alpha plus beta plus gamma prime, or the negative of those 3, should be equal to the number in front of, or the coefficient of, my x squared. That was shown up above, right? So what I should be able to do is say that minus alpha plus beta plus gamma prime is equal to 1. Okay, and then I can say that if I rearrange this, I can say minus gamma prime is equal to 1 plus alpha plus beta. Okay, so my gamma prime is equal to minus 1 plus alpha plus beta, but they asked for it in terms of gamma, and remember from earlier, alpha plus beta plus gamma is equal to 0. Okay, so this is the previous gamma, and this gamma prime is another solution, another point. So if I put in alpha plus beta equals minus gamma, I can write this as gamma prime is equal to minus 1 minus gamma, and that is just equal to gamma minus 1. Okay, so this new point, this new sort of point where the curve up above and our new circle where they cross is at gamma minus 1, and because gamma minus 1 is not a solution to x cubed minus x plus 1/4 equals 0, there must be 2 y coordinates for that. So that's a further 2 points where the circle cuts that the weird blobby shape in the curve up above. Okay, so so that's the solution to this part. I think I've argued well that it will cut to 2 points, okay, and they've got a common x coordinate in terms of gamma. Yeah, we've done that. Good.